Okay, so last week we discussed hypothesis test. Section 1 is a large sample test for population mean, and also we learned how to draw conclusions based on the results. Okay. And also, all right, so this week we start with section 3, which is test for population proportions. Okay. For confidence interval, we also have a confidence interval for population proportions. Okay. And remember, a population proportion is just the population mean for a population of zeros and ones, okay, such as the Bernoulli population. Okay. For Bernoulli population, we have 0, 1, 0, 0, something like that. So when has nothing happens, fail, we call that 0, and 1 means is success. Okay, and here is example. We have suppliers of semiconductors, waffles, claims all waffles supplies no more than 10% are defective. Okay, and then he get a sample of 400 waffles and found out 50 or 12.5% are actually defective. So this is actually more than 10%. Okay, so can we conclude that the claim is false? Okay. So let's look at this example. Okay, so here we have a sample which has success and failures. Okay, and success means the defective waffle. Okay, and we get 400 waffles, and we found out 50 of them are defective. Okay, so that's the condition. Right. And if the population proportion of defective waffles, if we call that P, and then the claim is that P less or equal to 0.1, less than 10%. Okay, so no more than 10% are defective. Right. So here is the example we want to check if the population proportion actually less than 0.1, and we get a sample proportion which is 12.5%. Right. So the setup is like this. Let's define X is number of success in an independent Bernoulli trials. Okay. And based on chapter 4, we know X will follow binomial distribution and P. N is number of trial, P is the success rate for each trial. Okay. And then the null hypothesis is 0. Okay. So depending on how the question is asked, can be set up as this. P is the population proportion less or equal to P0. P0 is whatever the question is asked. Or H0 is equal to P large or equal to P0, or P equal to P0. Again, how H0 is set up is depending on how the question is asked. Okay, and pay attention, again, all equality line go with H0. So this is true for all different scenario in chapter 6, hypothesis test. And also we have one more condition. More students join. So one more condition is both NP0 and N times 1 minus P0 are greater than 10. So much that this is based on the condition for central series, but doesn't really matter. But this is the condition should be met. Okay. What we need to calculate is the z-score. Okay, so this is the z-score. Here is the sample proportion. This is the sample proportion. Okay, and P0 is depending on what the question is asked, and N is the sample size. Okay, so we calculate the z-score. And then we calculate the p-value, right? So, but that is depending on how H1 is set up. So if H1 is set up is population proportion P larger than P0, okay, then the p-value is the area to the right of Z. Less than P0, area to the left of Z. Not equal, then the p-value will be the sum of the two tails. Okay, cut off by Z and minus Z. So this is the same as other situations, such as large sample population mean. Okay, so the same setup for H1. All right, and then let's look at the waffle example and do the calculation. Okay, again, the claim is no more than 10% are defective, and actually we get a sample of 400 waffles and found out actually 12.5% are defective. So let's first set up H0 and H1. Okay, so remember, whatever the question is asked, it should be H1. Okay, the question is asking, can we conclude that the claim is false? Okay, and this should be H1. So what is the claim? The claim is this. The claim that all waffles supplies no more than 10% are defective. Okay, so that's the claim. So H1 will be set up as P, which is population proportion larger than 0.1. Okay, so the claim is false. Claim is false. And then H0 will be the opposite. So H0 will be population proportion less or equal to 0.1. Okay, remember equality line always go with H0. Okay. So that's the setup. Remember, based on central limit theorem, okay. Sorry. Where is it? Okay. Based on central limit theorem, sample proportion, sorry. We'll follow up a normal distribution, okay, like this. That's the reason why we need to calculate the z-score like this, okay? And we call that null distribution, okay? Null distribution. Okay, so we set up H0 and H1. Sorry, this is H1. So, and we assume H0 is true, and we got a null distribution. Okay, and then we can calculate the z-score. So the z-score is equal to sample proportion minus P0, and this is P0, 1 minus P0 over N. This is the sample size. Okay, and sample proportion here is, you get 50 waffles defective over 400. So that is 0.125. Okay, and P0 will be 0.1. So P0 is 0.1, and sample size is 400. Okay, so based on that, we calculate the z-score. Z-score is 1.67. Okay, and then let's calculate the p-value. All right, so it's depending on how H1 is asked. So if p is larger than 0.1, as we see here, larger than p0, the p-value is the area to the right of z. Okay, so we're going to use the z table. The z table is table 8.2. Okay, p0 is 0.1. So this is for sample proportion of 0.125, which is corresponding to a z-score of 1.67. Okay, to the right of z, so which is the area to the right of z. So from the table 8.2, we calculate this area, the p-value is equal to 0.0475. Okay, so the question didn't tell us the alpha. Okay, remember, we need to compare the p-value with alpha. So if the question didn't tell us the alpha, we use alpha of 5%. Okay, so 0.0475 is just barely less than alpha. So then we can draw the conclusion, because p less than alpha, so we would reject H0. Okay, so we conclude H1 is true. H1 is true. So, and H1 is, the claim is false. So we can conclude the claim is false. Okay, so you can see the procedure is exactly the same as we discussed in section 6.1. So first of all, we set up H1 and then H0, depending on how the question is asked, actually where it is last sentence. So can we conclude that whatever after conclude will be H1? Okay, then we set up H0, and then we calculate the parameters. In our case, the z-score based on this equation. Okay, and then we calculate the p-value and compare the p-value with alpha. If the p-value is less than alpha, then we reject H0 and we say H1 is false. If the p-value is larger than alpha, then we cannot reject H0 and we say H0 is plausible. Okay, but we never conclude H0 is true. Okay. Right. So that's the first example for today. Here is another one. Okay, so the article presents a method for measuring orthometric height above sea level. And we have a sample of 1225 baseline. Out of this, 926 gave result that were within the class C spirit leveling tolerance limit. Okay, so whatever the question. But we know 926 out of 1225 is a proportion. So can we conclude that this method produced result within the tolerance limit more than 75% of the time. Okay, again, first of all, I would look at the last sentence and see what the question is asked. Okay, so the question is asking, is this method produce result within the tolerance limit more than 75% of the time? So this will be H1. Okay, so H1 will be the P0 larger than 75%, so 0.75. So H0, on the other hand, will be opposite. So H0 will be P less or equal to 0.75. Okay. So the sample proportion from the question will be 926 over 1225. Right. So we calculated the z-score based on the equation. So the sample proportion minus P0, so this is P0. P0 1 minus P0 and sample size. Okay, so the sample proportion is this. Okay, the P0 is 0.75. Sample size is 1225. Okay, so we calculate the score, which is not very big, 0.48. Okay, 0.48. Again, depending on how H1 is asked. Okay. And we calculate the p-value. For 0.48, so H1 is P0 larger than 0.75. So P is areas to the right of Z, to the right of Z. Okay, so the p-value from here, the table 8.2, we found out as 0.3156, so much larger than 5%. Okay, so which is, let's see, larger than alpha. Again, the question didn't tell us the alpha, we use 5%. Okay, so p-value larger than alpha, so we conclude we cannot conclude H0 is false. Okay, so we cannot conclude the method produce result within the tolerance limit more than 75%. Okay, so we cannot conclude H0 is false, which means H1 is true. Okay. All right. So that's the conclusion. So we cannot conclude that the method produce result within the tolerance limit more than 75% of the time. Okay, so again, depending on how H1 is asked, okay, so here the case larger than the value, so we use right of Z, okay, so depending on this situation. Okay. All right, so that's section 6.3. The next one is small sample test for population mean. All right. So from central limit theorem, chapter 5, we also have small sample confidence interval for population mean. Okay, and we learn from there, we're gonna use students' T distribution instead of Z table. Okay. In section 6.1, we have a large sample. Okay, population mean. Right, and then we use sample standard deviation S to replace population standard deviation sigma. because the sample size is large. But when the sample size is less than 30, S will not be close to sigma. Okay? And that's the reason we should use students' T distribution. Okay. And here it says, if in a case we do know the population standard deviation, then we should not use students' T distribution. Then we should use the normal distribution, the Z table instead. But this is a special situation. Special situation. Okay. So only when the population sigma is known. Okay. So if x1 to xn is sample from a normal population, okay, so for small sample, we have one more condition. Okay, this is the population has coming from a normal distribution. Normal distribution. Okay. All right. And if we do not know sigma, H0 will be set up as this. Okay. Again, all equality line go with H0. Depending on how the question is asked, we can set up H0 like this. Mu less than equal to, large or equal to mu 0. And we calculate t value. Okay, t value. So this is the sample mean. Mu 0 is depending on how the question is asked. S is the sample standard deviation. N is the sample size. Okay, so calculate the t value. And then again, depending on how the question is asked, or the H1 is set up. Larger than mu 0, P value is area to the right of T, okay, not Z, right of T. Okay. So less than mu 0, P value is area to the left of T. Not equal, then will be 2 tails cut off by T and minus T. Okay, you can see it's exactly the same setup as we hope to calculate the p-value. Okay, here is an example for that. Before a substance can be deemed safe for landfilling, its chemical properties must be characterized. Article report that in a sample of 6 replicates of sludge, okay, from a wastewater treatment plant, the mean pH value was 6.68, okay, with standard deviation of 0.2. So that's sample standard deviation. This is the sample mean. Okay. So can we conclude that the mean pH is less than 70? Okay. Again, this goes to H1. Okay. So H1 will be the mean value, the population mean value less than mu 0, which is 7.0. So H0 will be the mean large or equal to 7.0. Okay, so we set up mu and H0 and H1. Okay, then we calculate the t-score. The t-score is the sample mean minus mu 0. Right? Okay. The sample mean is 6.68. Okay. Mu 0 is 7.0. Sample standard deviation 0.2. Sample size is 6. Okay, so we calculate the z-score minus 3.92. Then we can find out the p-value. Okay, the p-value depending on h1 is minus mu 0. Okay, minus mu 0. Okay, it should be on the left. Okay, but let's look at the z table. Okay, sorry, not z table. The t table. All right. Okay, so here is the table upon 3, the student's t distribution. All right. So we calculate the t value, which is minus 3.92. 3.92. Okay. So for the t table, it didn't give any possible values. But before we do that, remember for the t table, we have degree of freedom. The degree of freedom is depending on the sample size. The sample size is 5. Okay, so 5. Sorry, let me go over here again. 5 minus 1, which is n minus 1, is equal to 4. Okay, so that is the degree of freedom equal to 3. So we look at table 8.3 for degree of freedom of 4. Okay, and then the value of t is minus 3.92. Okay, but only we have the positive values. Okay, but 3.92 is between 0.01 and 0.005. Okay, because for 0.01, this is 3.747. For 0.005 is 4.604. Okay, so it's between 0.01 and 0.005. Okay, so what this mean here is here. All right. So this is the t distribution. Okay. So the t value is minus 3.92. Okay. And we found out for positive 3.92, the alpha is between 0.01 and 0.005. Okay. So for minus 3.92, because the t curve is symmetrical, okay, symmetrical to 7.0. So that means it will also between 0.05 and 0.01. Okay. Here it is. Okay, so the t-value of minus 3.92 will be these areas, which is between 0.005 and 0.01. Okay, so we cannot get the exact p-value, but we know it is between 0.005 and 0.01. Okay, so that is good enough. So that is p-value less than alpha. So we can conclude that we can reject E0 and conclude H1 is true. So yes, we can conclude the mean pH less than 7.0. Okay, so we conclude H1 is true. H1 is true. Okay. All right, so that is the student's T distribution. Again, we calculate the degree of freedom, okay, which is n-1, and then we look at the table 8.3. Table 8.3. Okay. So that is section 6.4. 6.5 is a large sample test for the difference between two means. Okay, so we also do the same thing, large sample test, not test, confidence interval for difference between two means. Okay, here we are interested in if the mean of the two populations are equal or not. Okay, and we get two samples. Okay, two samples from two different populations. Okay, if the difference between these two samples are far away from zero, then we say the population are different. If the difference are close to zero, then we say the two population means could be the same. Okay. And here is the setup. So if x1, x2, xn are one population, and the y1, y2, and yn another sample from population, and the sample size is large. Okay, so that's the condition. And if they are coming from population with a mean value of mu x and mu y, and the standard deviation sigma x and sigma y, okay, and then these two populations are independent to each other. Okay, so here it says from a population, but doesn't say is coming from what type of population. So no matter it is normal distribution or not, okay, so no matter normal or not, the following equation will hold true. Okay, so any population will be okay because the sample size is large. And here is the setup for the hypothesis test. So H0, the mean value of x and y, less or equal to delta 0, okay, or large or equal to, depending on how the question is asked. But again, the equality line always goes with H0, as you can see from here. And then we calculate a z-score. The equation is different. Okay, this is the sample mean of x, sample mean for y. This is delta 0, depending on how the question is asked. If the question is asked if the two mean values are different or not, then this could be 0, for example. Okay, this is population standard deviation for x and y, and this is the sample size for x and y. Okay, we can use sample standard deviation x, sx, and sy if we do not know population information. Okay, right. And this is how we calculate the p-value, almost exactly the same, depending on how h1 is set up. H1 is set up as larger than delta 0, then p-value is to the right of z, less than left, not equal to cut off by z and minus z. Okay, so exactly the same as before. Okay. So the procedure, as you can see, is the same. The setup is the same, but we just use slightly different equations. Okay. So which equation to use is depending on how the question is asked. Okay, if it's large sample, in this case, is the difference between two means. Okay. So here, article compare properties of vents. Okay, made using two shedding gas. One is carbon dioxide. The other is using a gas of argon and carbon dioxide. Okay, so this is the shedding gas for weld. One property study was diameter of inclusions, okay, which are particles embedded in the weld. Okay. A sample of 544 inclusion using argon shedding gas average this much. Standard deviation of this. Another sample, 581, using carbon dioxide gas, okay, we has average of 0.4 micrometer and standard deviation of 0.26 micrometer. Okay, the most important is last sentence. Okay, can we conclude that based on this, we know this is hypothesis test. So this is chapter 6, right? And then what the question is asked, this is the mean diameter. This is population mean, right? The mean diameter of inclusion differ between the two shedding gas. So this is the difference between two means. The difference between two means, and the sample size is large. Okay, so we see this is large sample hypothesis test for difference between two means. So the equation we're going to use is in section 6.5. So we calculate z-score like this. All right. So again, whatever after the conclusion will be H1. Okay. So first of all, let's set up X and Y. So let's see one gas, mean is 0.37. The other one, we call that Y. Sample standard deviation, sample size. Okay. So whatever asked the after conclude will be H1. So H1 will be the mean value difference not equal to zero, because differ between the two shedding gas. If that difference, then it is not equal to zero. And also, because the equality line always go to H0, so H0 will be mu x minus mu y equal to 0. Okay, so here 0 will be the delta in the equation. Okay, so then we calculate the z-score. The z-score, the mean value difference for the sample. Okay, so 0 will be the delta 0 here, and we get sample mean for x, sample mean for y, okay, sx here, sy here, okay, and nx and then y. So everything is here. So we calculate the z-score is minus 1.97, minus 1.97. Okay, and because the h0 is asking not equal to 0, not equal to, so not equal to tells us the p-value will be the sum of the two tails, sum of the two tails. So because this is the z-score, all right, here, all right, minus 1.97, the other one is minus z, so 1.97. The cutoff, the two value added together, so the p will be 2 times 0.0244. So the p value is 0.0488. All right, so less than alpha 5%. So we can reject H0 and we see H1 is true. Okay, H1 is true means yes, we can conclude that the mean diameter of inclusion differ between the two shading gas because we set up whatever after the conclusion will be H1. Okay, so H1 is true. All right. So the last section we're going to discuss is section 6.6, which is hypothesis test for difference between two proportions. Okay, so the procedure is the same, but just a little bit different in the equations. Okay, so the proportion we know is belong to binomial distribution. Okay, so if we see we have two population and they follow two different binomial distribution, okay, nx px and ny py. Okay. Okay. And then we might consider the null hypothesis for the population proportion will be larger to 0. Okay, then H1 will be less than 0. Okay, and we do the hypothesis test based on a sample proportion, px and py. So the sample proportion px and py. And then we set up a null distribution. Okay. Based on the central limit theorem, this is section 4.11. Okay. When the sample size is large, okay, and the sample proportion will follow a normal distribution. Okay. And here will be the null distribution. Oh. Okay, so let me write this down. So it should be the sample proportion px minus py follow a normal distribution the mean value is px minus py. The sigma squared, the variance will be this. Okay, sorry, when I print the PowerPoint slide, something wrong with here, but it should be this. Okay. To get the known distribution, we must substitute values from the mean and variance because we do not know the population mean and variance. Okay. The mean value is 0. Okay. So that's simple. But the variance will be a little bit more difficult. We're gonna use another parameters, which is called pooled proportion. The pooled proportion is defined as this. Okay. So the pooled proportion the equation is this. Okay. So that is dividing the total number of success in both samples. So x plus y divided by the total sample size, nx plus ny. So that's called pooled proportion. It's kind of average of these two proportions. Okay. So the known distribution will be this. Okay. So mean value is 0. This is pooled proportion, which is equal to here. The sample size nx and n1. Okay. All right. Let's look at the setup. If x follow binomial nx px and y follow binomial ny and py, and we have at least 10 success and 10 failures. Okay, so this is a condition. And also another condition is these must be independent. Okay. And then depending on how h1 is asked, so h0 will be the difference between px and py less or equal to, large or equal to, or equal to 0. Okay. And then we calculate the sample proportion, px, sample proportion, py, and then the pooled proportion, okay, depending on the success of x, y, and sample size. Okay. And then we calculate z-score. The z-score is this. Okay. Yeah. And then the setup of each one will be almost exactly the same. Px minus py larger than 0, the p-value will be right of z, less than left, not equal, 2 tails cut off. Okay, 2 tails cut off. All right. So that is the last example for today. So industry firms often employ method of risk transfer, okay, such as insurance or indemnity clause in contract, okay, as technical of risk management. Article report that result of survey in which manager will ask which method play a major role in risk management strategy of their firms. Okay. In a sample of 43 oil company, 22 of them say the risk transfer play a major role. In another sample of 92 construction companies, 55 report that risk transfer play a major role. Okay, so we have 2 samples. One is from oil company, another from construction company. So we have 2 proportions. One is 22 out of 43. The other one is 55 out of 93. Say the risk transfer is important. Okay. So the question is asked, can we conclude that? Again, you know, this will be H1. H1. Okay. So can we conclude that the proportion of the oil company that employ method of risk transfer is less than the proportion of construction company that do? Okay. So let's define. Okay. For the oil company, that is X. Sample size is 43. 22 of them said play a major role. So the sample proportion will be 22 out of 43. The construction company, we call that Y. Sample size is 93. 55 of them say play a major role. So PY will be 55 out of 93. Okay. So let's set up H0 and H1. Okay, so again, this will be H1. So that means Px minus Py will be less than 0. So the proportion of oil company, the X, is less than the proportion of construction company, the Y. So Px minus Py is less than 0, so which is equal to Px less than Py. Okay. So then H0 will be the opposite. Px minus Py large or equal to 0. Okay. Then we calculate the z-score. But before we do that, we need the pooled proportion. The pooled proportion is this, based on the equation. Okay, so the z-score is this. Okay. Which is this. Px minus Py 0.5914, this one. Okay. Px is this. Square root of this is pooled proportion. This is sample size 43 plus 1 minus 93. So plug in the number based on the z-score. So the z-score is actually z-score is calculated as minus 0.87. Okay, minus 0.87. Right. So because H1 is less than will be, the P value will be to the left of Z. Okay, because right, less than 0, P value is the area to the left of Z. Okay, so you get the idea now. So left of Z for Z value of minus 0.87, so the P value is pretty large, 0.1922. So which is larger than 0.05, which is the alpha if we do not tell alpha is what in the question. So we assume alpha is 5%. So the answer is no, we cannot conclude. So we cannot conclude that. You just repeat the last sentence. The proportion of oil company is less than proportion of construction company. Okay, so that's the conclusion. All right. Any questions before we dismiss today? We have probably one more, as you see, one more lecture for chapter 6, and then another lecture in chapter 7, and we are done for the formal lectures. Okay. Any questions? If no, gonna see you next time.